All right. Estimation and confidence intervals. Does everybody remember doing this? What are we talking about here? So, it's two separate ideas that tie together, isn't it? So what is a point estimate? Who remembers what that is? A point estimate. So if I have a So if I have a population that I don't know anything about, okay, and I take a sample of that population, and let's use the point estimate of the mean, okay? I take a sample. I want to know the mean of the population. Well, like I said, I don't know what it is in reality, but I just took a sample, didn't I? So what's the best guess I have at this point as to what the mean of that population is? That's right, the mean of the sample. That's all we have to go off of right now, isn't it? But it's only one sample, so do you think it's going to be that accurate or no? No. Probably not. Could be, who knows, but probably not. Can't assume that it is for sure. What is the difference between that point? Okay, so that serves as the point estimate. The estimate, the best estimate we have, right, of that point. The point being the mean. Are there point estimates? Can we use any statistic as a point estimate of the corresponding parameter of the population? Yes. Everybody understand that question? Okay, yeah, so we can. Standard deviation can be a point estimate, can it? Yeah. All right, so what's the difference between that point estimate and the actual, if we were to know the actual? Who remembers that term?
Standard error.
Not the standard error, but something else, similar. Something error. Sampling error, very good. Because it's the error from, that we got by taking that sample, didn't we? Remember? Okay. All right, so these things end up looking like this, don't they? So far we've looked at how to do these with the mean, haven't we? So we said we got these distributions, right? That's the population. And we're saying, well, we don't know anything about this population really, but we took a sample out of there, didn't we? And for this sample, we got this average, didn't we? This point estimate. So we already said, look, I don't know how accurate that's going to be, right? But what do I do in order to give myself a little leeway? Huh? Well, what's the other part of what we're studying? The point at the estimation, and what's the other part of it? The title we just looked at. What?
Oh, the confidence interval.
Right, so we do those confidence interval problems that we've been looking at, right? And those are all x bar so far we've looked at of the mean is x bar plus or minus something. Plus something or minus something. Remember? What do we call these? This is the chapter we're on, right?
Yeah.
Just making sure, okay. I get turned around sometimes. What do we call these? The starfighters, right? From Stargate or Star Wars, whatever, right?
Don't you get on those?
Isn't that what we were talking about last semester?
Yeah.
Is it Star Trek or Stargate? I don't remember.
Well, which one are we talking about again?
The TIE Warriors or whatever.
Star Wars.
Star Wars.
Star Wars.
Okay, just making sure.
Yep.
I remember that really upset you.
Mm-hmm.
Oh, maybe that's why you never came back.
Yeah.
All right. So do we remember this example right here? The Bureau of Tourism in Barbados, remember we took that sample 500, came up with that average, that X bar. We said, well, that's probably not right on the average that they spent, but for our example, what we said was it's probably $500 one way or the other, isn't it? And remember, we eventually got to where, with that actual confidence interval, we said we're 95% sure that the mean of the population, again, this is the sample over here, that's the population there. The population will fall between that and that. Remember? Okay. So, the confidence intervals, right? So range of values constructed from the sample data, from our sample size, our standard deviation, and our desired level of confidence. Those were the three factors that made up that formula. Everybody remember that? Sometimes we do know what? Oops. Sometimes we do know what? What does that title say? After that comma, that second clause there, what does that say?
Your sigma known.
Very good. The what?
Population standard deviation?
Very good, the population standard deviation. Sometimes we do know that, sometimes we don't, right? When we do know the population standard deviation, we use that formula right there, remember? We got our X bar, the average from that sample, and we go plus that figure minus that figure. That figure being what? Z times what? What is that thing right there? That shoe company? Didn't we look at that?
Yeah.
Sigma over the square root of n. The big one I told you to burn into your brain. You already said it once. Your
Oh, is that your standard error?
standard error.
Yeah, that's right.
That's the standard error right there.
Yeah.
Right? Every time. I was waiting for you to say it, man. All right, so Z times the standard error, which makes a lot of sense, doesn't it? It's essentially your confidence times your right-sized deviation. Yeah? Your deviation, which is right-sized by the sample, for that particular sample. Makes sense, doesn't it? Okay. But then there's also times when we don't know that... actually, first of all, let me ask you something. What is the most common confidence interval we use? Who remembers? Yeah, very good. So that represents what percentage of the area under the curve? The normal
45.
Z curve, huh?
45.
No, 95.
Half.
Huh? Right, I know what you're saying. 47 and a half
Yeah.
brings you to that 1.96. But
Almost so.
that 1.96 is, it's actually 95%. Because remember what we used to say for the empirical rule? Remember that? What is, to one standard deviation, what percentage of the area under the curve are we talking about? All your data. 68%. 2 is what? 95. 3 is what? 99.7. Right? So we used to say 2 is 95% of all that data. But now we know it's actually not 2. That was just an easy way to say it. What is it precisely? It's what? More precise. It's 1.96. Yeah? Okay. So again, anytime you have that 95% confidence interval and you have a Z, you're using the Z-score, right? It's 1.96 every time. So please don't keep looking it up. Just remember that. I know somebody's going to do that. They're going to keep looking through the book. And they're not going to notice the pattern that they're getting the same answer every time. You know why I know that's going to happen? Because that was me once upon a time. No, I'm just kidding. I wasn't even that dumb. Just know it's 1.96. Also, what was at the top of that chart I'm going to give you guys?
The 1.96.
Yeah, so this precise example, remember, right here, is at the top of the chart, isn't it, that you're going to have on your test. So even if you forget the 1.96, it's already written on there for you, isn't it? And what's another way? You can use the empirical rule. If you can't remember exactly, you can be like, well, I know it's close to 2, and hopefully that'll jog something, right? Because 95% of the area under that curve is 2 standard deviations, remember? That's your mean, 1, 2, 3 standard deviations, 1, 2, 3 standard deviations, and up to this 2 is 95% of your data, remember? Okay. All right, so if we do not have that known sigma, what do we use for it? Who remembers? We got a point estimate for that, don't we, for our sigma? If we don't know the standard deviation of the population, what can we use for the best substitute we have?
Your sample standard deviation.
Yeah, our sample standard deviation. We know we're going to have that, right? Because we took the sample. We can figure out whatever's about the sample we want. Can't we? Yeah? But that's not going to be right on, is it?
No.
But we can still use it for the point estimate, can't we, of the standard deviation? Okay. So, when we use that S though, remember this is the same formula, isn't it? Doesn't it look just like that one? They look exactly the same, don't they? Except for what? Instead of that sigma, we're using the S. And if we use that S, we can't use the Z, can we? What are we using?
T.
T, very good. Everybody with me? You with me? All right. So if we're using that T, we can't use the Z table, can we? But we have another chart we can use, don't we? Remember that? Y'all probably don't remember that, but look through it, you'll be fine. It's really not too tough. All right. We have another chart we can use, which is what? Yeah. That T table right there. Students T, remember? All right, so how do we use this sucker right here? Who remembers? How do we use that table right there?
You define one of those three above.
Yeah, so we're ignoring these bottom 2 rows, aren't we? Bottom 4 rows, really, but they're two different, levels of information. But we're using the confidence intervals on top, right? And we're interested in 95% most of the time, aren't we? And we bring it down how far? Well, this one comes to 9. So if that's 9, what can you tell me about the sample size of the problem? It's 10, isn't it?
10 minus 1 for samples, right?
Yes, very good. And what is that called? The sample size minus 1 is called what?
Degrees of freedom.
Very good. Degrees of freedom. Remember that? DF. When do we use sample size plus 1? Never. Very good. When do we use sample size plus 10? Huh? What did you say? No, what did you say? No. Never. When do we use in minus 10? Never. What is it? Always, always, always. In minus 1. So, it's always. So which ones should we memorize on this one? Huh? None of them, really, right? Why is that?
It's always different.
It's always different due to your sample size, isn't it? There's not necessarily going to be one sample size that's more common than another, is it? In fact, we'll look at how we need to calculate our sample size today. Okay? We're going to look at the formula for that here in just a minute. So we had an example here. And this is where we're going to pick up our new information, all right? And y'all are not going to believe this, but I actually put, do you remember that last Excel sheet, the big long one that I sent you guys? Open that up real quick and actually put the Excel that we're going to use on that sheet, okay? And I'll be right back, all right? So go ahead and open that up. All right, did y'all find it? Hey, you know what? I was just thinking about it. It's actually not on there. So never mind.
Yeah.
Yeah. I just remembered. All right. So, confidence intervals per proportions. Who did find it, though? That's not really fun. Confidence intervals for proportions. So, what are we talking about here? What were we just doing the confidence interval for? Who remembers that? What we just did? For the mean, though, right? So what were we doing? Again, we were saying, we don't know where this mean is. We want to know where the population mean is. We don't know where it is, but we took this sample, we got the mean, and we're going to say the mean is here, where the mean of the sample is, plus or minus a bit, depending on how confident we want to be about it, right? And hopefully, we are going to be 95% sure, let's say, that the mean of the population falls from here to here. Right? Okay. Okay. So we can do the same thing with proportions. All right? What are we talking about with proportions? Let's look at the formula first real quick. Well, let's look at the definition. Fraction, ratio, percent indicating the part of the sample or the population having a particular trait of interest. That sounds a little bit familiar, doesn't it? A favorable trait, let's say, that we're looking for. Let's look at the formula right there for sample proportion. P equals what? X over N, this sample size. Yeah? Or it could be pi in Greek for the sample, right? For the population, it could be what? Pi equals X over capital N, nu, right? Okay, have we heard that before? Anywhere before? Maybe like favorable over total? Does that ring a bell, that formula? That's our base probability formula, isn't it? Very good. We've seen that before. Remember the favorable, what we're looking for over the total. Remember? So that's all that formula is, isn't it? It's the same as the probability formula. It's just we were looking at probabilities before. We're looking at samples to populations now. Okay? So, when I'm talking about a proportion, what am I talking about? Let's look at this example right here, first of all. That's on the screen. What does this say right here? Because I want you to notice a couple characteristics about it. So let's just say we got a normal distribution, yeah? And let's do this example real quick. Southern Tech Career Services Center reports that 80% of its graduates enter the job market in a position related to their field of study. Okay? Let's say we had 1,000 people graduate, and they're right on the average. Last year we had 1,000 people graduate, and they fell right in line with the average. Of that 1,000, how many people would have found a job in their field if they held to that true average?
50%.
Huh?
80%.
Right, so how many is that out of that 1,000?
800.
800. All right, does everybody understand that? So where is 80% of the proportion in this normal curve? Where would that be? It'd be like, wouldn't it be like up to here, right?
Yeah.
Is that where you're pointing? I couldn't tell because.
That's why
Okay.
I was like, yeah.
All right.
I was trying to- outside, and I was like, he's kind of in the way of it.
All right. So this would be 80% right here, let's say, right? Okay. If that's 80%, what is this?
20.
20%. What is 80% plus 20%?
100.
100, isn't it? Okay. Simple concept, is it not? Just wanted to remind ourselves of the rule of complements, stuff like that, okay? All right, so the proportion is what we're interested in over the total. So in this case, it would be 800 out of that sample size of 1,000, wouldn't it? Or population, however you want to say it. Same formula, just depending on what you're talking about, right? Everybody with me? Pretty simple so far, right? Okay. Now, we can do the confidence interval of this is just that example. We can do a confidence interval of the proportion just like we did with the mean. Okay, what I mean by that is, for instance, let's say that this 80% right here, the graduates from Southern Tech, we don't know what that actual population proportion is. Okay? We might think it's around 80%, but we don't know, do we? Okay? So what are we going to do to figure out something about the population? We're going to take a what? Sample. Very good. And we can look at that sample, and in that sample we can look at what? If we want to know about the proportion who get a job in their field, what can we look at in the sample? The proportion. In that sample, who got a job in their field, couldn't we? We could look at in the sample what we want to know about the population, right? Okay, now. Blah, blah. Okay, so. What would our Star Trek fighter look like if we were going to do a sample of the proportion instead of the mean? So it's still going to look like that, isn't it? But is this going to be X bar? What is this going to be? Huh? No, because we're not dealing with averages anymore. We're dealing with proportions, right? We're not dealing with where does this thing average out. We're dealing with how much of this curve is to what side.
Wouldn't that just be your P?
It would be your P, wouldn't it? This is your sample proportion, and from your sample proportion, we're going to try to find out what the population proportion is, okay? And we're going to use that sample proportion, not the mean, but the proportion to figure out more or less where that sample proportion is going to fall. Now, what does this say right here? Who remembers the binomial conditions when they refer to that, what they're talking about? So we did not do chapter 6, did we? But we did do what with those binomial probability distributions? We approximated them. Do you remember the approximation of the binomial that we did? And when we did that part of that chapter, I think it was chapter 7, what did we talk about with this we looked at chapter 6 for a minute to look at what a binomial probability distribution is, didn't we? And it had to meet several characteristics. What are those? First off, how many outcomes can there be? 2, right? Binomial, right? 2 possible outcomes. Is that what's holding true for our proportions right here? Well, yeah, it is. It can be either they got a job in their field or they didn't get a job in their field,
That's true.
right? What you were thinking is 50-50.
Yeah.
But we're not talking about that, are we? We're just talking about
More of
2
the,
possible outcomes. Okay? You were thinking bimodal,
yeah.
not binomial, okay?
Yeah.
Now, what else? What were some other rules with that? Who can remember this? So we're flipping a coin, which is 50-50, but okay, so we'll flip a coin. We got 2 outcomes, right? So let me ask you this. Remember this one? We're doing an experiment of 5 flips. First 4 we flip tails. What's the 5th one going to be?
Either.
What are the odds that it's going to be a tails?
50.
50%. What are the odds it's going to be a heads?
50%.
But wait a minute, we just had 4 tails, so the 5th one should be a heads, right? It's got to even out a little bit.
They're independent.
Huh?
Each test is independent.
Independent. Each experiment is independent of the previous ones, isn't it? Right? Okay, very good. So isn't that another condition? We need independence, don't we? The third most important would be what? I guess it would just be defined number of trials. You have to set the number of trials, okay? All right. But the big thing is we're talking about splitting this area under the curve into 2. All right, that's it. And where we split it into, this is the yes, this is the no. This is the did get a job in their field, this is the didn't get their job in their field. Or vice versa, but I'm just saying they're opposites, right? 2 outcomes, 2 possibilities, okay? All right, now let's look at this other condition right here. The values of, what is this right here? N times pi. What is N? Is what? Sample size. What is pi? Okay, that's Latin P. What is proportion? This is sample to proportion. This is Latin P. What's Greek P? Yeah, it's pi. But so what is pi? What does that mean? Greek. If it's Greek and it's the P equivalent, what does it mean?
Population.
It's the population proportion, isn't it? Remember Greek population, Latin sample, right? City versus country. All right. So the value of the sample size times that population proportion, right? Times however many are over here. And also the sample size times 1 minus P, the proportion of the sample, which is what? The rest of the curve, isn't it? Both have to equal 5 or more. But not, I'm not talking about 5% of the total. I'm not talking about anything like that. I'm talking about literally the number 5. Okay? Why is that, do you think? Essentially, what that does is make sure we have a big enough sample size to where the normal probability distribution, the normal Z curve, will hold true. Okay? Anything smaller than that, and we're talking about proportions so small that they don't hold the form. Okay? Just remember, it has to be bigger than 5. Okay, both of those. All right, now. Before you do any of these, you need to test that those conditions hold true. Okay? Everybody hear me? Fortunately for you, in your book, they do. I mean, for the most part. I don't know if I've seen one where they don't, or even that explicitly asks you. Is there one? Have you seen?
I haven't seen any.
Yeah, I don't think they do. So you can just assume that they meet the standards, okay? Before you do one of these problems. All right. But let's look at the formula here. P, what is that? Little Latin P, right? Plus or minus Z. At 95%, that Z is going to be what? 1.96. Very good. And we're going to multiply it by what?
Square root.
The square root of all this stuff, right? P times 1 minus P. Yeah, P times the rest of the everything else over the sample size. But let's look at what is that saying right there, plus or minus. So we already established that this proportion, we got it from the sample, right? Because we don't know what the proportion for the population is, do we? So we got it from the sample. It's our point estimate. Best thing we got to guess off of, right? Plus or minus this. Okay? So we're about to do an example, but before we even do it, we're going to remember we write out our variables from here on out, don't we? We always write our variables out. So, I'm going to erase all this. So what variables do I need to write out? What variables do I know that I'm going to have to fill out? P. What's another one? Huh? N. Very good. What else?
Z.
Z. But there's one more up there that you're not seeing that we looked at before. Where do we get that P from? If it's not given to you, that is. We get the P from there, don't we? So what's another variable we're going to have to know in order to solve for this? The X, which is our favorable, what we're looking for, right? Okay. So X. And I'm going to put the X right here, actually, okay? Because we're going to put X over N, aren't we, to make the P. All right? And we know we're going to need our Tide Warrior here from Stargate. Generation 2 or generation what? Stargate generation something. Beam me up, Spock. All right. So let's do this example right here. And we know this, by the way, we know this dot right here is going to be a what?
Point estimate.
It's going to be a point estimate. Very good. Of what, though? The mean?
It's the sample. The sample portion.
Sample mean? No. We're doing what right now? We're doing these, aren't we? Proportions. We're not doing means right now. So before we were finding where that average fell in here. Now we're going to find where that dividing line between the proportions falls. Okay? So this is going to be our P, isn't it? All right. So let's look at this problem right here. The union representing the bottle blowers of America. Big time. Is considering a proposal to merge with the Teamsters. Who knows who the Teamsters are? The old trucking union, right? Who's ever heard of Jimmy Hoffa? You ever heard of Jimmy Hoffa, the old mobster?
Yeah.
Yeah, buried under Jet Stadium out there in Meadowlands. That's where they think he's buried. Teamsters, actually, the federal government took them over. They were so corrupt for 25 years, and they're just letting them off. They're just spinning them back out this year. So Teamsters are on their own again. But I'm sure they'll be watched closely. Anyway. So the BBA is thinking about joining up with the Teamsters. But to do that, at least 3/4 of the BBA membership must approve the merger. That seems significant. I don't know where that's going to go in this problem, but I'm going to keep it in the back of my mind. Okay? 3/4 have to approve, okay? How much is that? Percentage-wise?
75.
Just to have it written down. 75%, isn't it? 0.75? Okay. I don't know where that goes yet. It might not go anywhere. Who knows? Let's see what we're being asked, okay? Okay. So at least 3/4 of them have to apply a random sample of 2,000 current members. That's a big sample, isn't it? How many members do you think they have if that's an appropriate sample size?
Millions.
That must be a big union, huh? I don't know. We'll learn how to, like I said, we'll learn how to figure sample sizes today, but must be a pretty big union. All right. So a random sample of 2,000 current members reveals, oh wait, random sample of 2,000 current members. That sounds like a variable to plug in somewhere. Where would that go?
Yeah.
In, very good. A random sample of 2,000 current members is sampled, and it reveals that how many plan to vote for the merger? For the merger. 1,600. So that would be my what? That's my X, isn't it? That's my favorable. I'm looking for how many are going to vote for this thing, right? That's my 1,600. Blah, blah, blah. That's all I got. What is the estimate of the population proportion? Can you conclude that it's going to pass or no? And why? All right. So I know that this is what I'm going to need. I'm trying to estimate my population proportion, but I don't know it. I want to know the pi. Don't have the pi. I got this p. What can I do with that? What is it? Huh?
You can figure it out by
How's that?
your X by your N.
All right. Did everybody see that? Remember that formula we were looking at? It was x over n, favorable over total, right? X over n is what? 1,600 over 20 over 2,000 is 0.8, isn't it?
Yep.
So let's plug that in right there. 0.8. Those go into that, don't they? Okay. So now I know what my point estimate is. 0.8. I know what my proportion is, at least in the sample. My sample told me that 80% of them are going to vote for it. Right? You think that's right on with the population? I don't know. But I bet I can be a certain amount sure, probably 95% sure, that it's going to fall between something and something around that estimate somewhere. Okay? All right. So, what does that next part say? Oh, we're going to use the formula 94. We're going to determine the 95% confidence level. How about that? Wasn't even giving it to us. We could have just assumed that, couldn't we? That's the one we're always going to use, pretty much, isn't it? Okay? So 95%. So that tells me what's my Z?
1.96.
1.96. Boom. Hey, guess what? We got all our variables filled out, don't we? We can solve this problem. What's my formula real quick? P plus n minus what? Z times the square root of what?
3 times 1 minus P over your N.
Over n. So let's plug and play. 0.8 plus n minus 1.96. The square root of 0.8 times 1 minus 0.8 over 2,000, right? And what's the answer going to be?
The calculator says
Point-
0.018.
0.18.
Plus or minus 0.018.
No. Plus what? And minus.
Yeah, plus and minus, that's right.
Yeah.
Plus or plus and.
So this is going to be plus 0.018. It's going to be minus 0.018, right? So this is what? 0.818? And this is 0.792? 82?
82.
Does everybody see that? So we got us a range here, but what does that range mean?
That means that there's a 95% chance that your desired outcome is going to be between those right there.
Well, that's right. So this is a range. We're 95% sure that the proportion where those people are going to vote for or against is going to be between 78.2% and 81.8%. Now let me ask you this. How many did we need for this thing to pass?
0.75.
We needed 75%, didn't we? Where's 75%?
Over to the left a little ways.
It's all the way out here, isn't it?
Yeah.
0.75. So if I'm 95% sure that the vote's going to fall within here somewhere, but all I need to have is that to pass, is it going to pass or not? It is, isn't it? Does everybody see this? This right here, this line right here at this X at 75%, this way, it's a pass, isn't it? This way,
It's a no.
oops, not a Z, an arrow, that's a fail, isn't it? Is our range over here where we're 95% sure it's gonna fall? Is that on the pass side or fail side? It's gonna pass, isn't it? This sucker's gonna pass. Do you think that could be useful in a business context?
Somewhat.
Probably so. Yeah? Okay. Does anybody have any questions about that? Do y'all understand what we just did? I know everybody understands it right now, and as soon as you get to the first problem doing this in your homework, you're going to be like, what just happened? Okay? That's why I ought to put these videos online, or on Georgia View for y'all to see. So you can go back to them and say, wait, how do you do that example? You know what I mean? Maybe I'll do that next semester. Got to make them first, don't we? All right. So we got our pass and our fail, don't we? And this one's going to pass. All right. We good? All right, let's keep going then. We do want to get out of here early today, right? What time are we looking at? 5:37? Out of what? 7 o'clock or something?
6 o'clock.
6 o'clock. 6 o'clock.
So we got 20.
And it's already 8:15, so we got.
So I don't know what we got. We're
We'll
gonna
have
test
20
on
minutes.
October 5th. Yeah,
Man, I ran my mouth too much today, didn't I? Let's burn through this. Sorry about that, guys.
that's all right.
Don't worry, I'm gonna get you out of here that 3 minutes early.
Don't worry. We're still early.
If y'all didn't take so long finding that exercise in Excel, we would have gotten out of here.
I know.
All right. So these I won't write out then, okay? We're just going to do these on the board. And the reason we're going to do these on the board is because I'd rather you understand the idea than the plug and play. Because they're straight up, you will be given the numbers you need for this. Okay? There's nothing funky in here about these, okay? But this is where we start determining how big of a sample size that we're going to need in order to get that accurate representation, okay, from our sample. That's going to be a true indicator of what's going on in our population, all right? So, determining the sample size for averages, for means, okay? So, 3 factors go into this. We got the margin of error, so that's something we haven't seen yet, that big E right there, right? But what is that margin of error? We've been looking at it the whole time. It's going to be this, isn't it? This is going to be given to us, isn't it? The margin of error. Okay? And it's going to depend on also what, though? Where's that next one? How sure we want to be, isn't it? So if we have the margin of error, and we have how sure we want to be, and we have how widespread, how different the variables are from each other within the population, we got everything we need, don't we? Okay. It makes sense. What else can there be that's going to skew how big that sample size is going to be? You see what I'm saying? Okay. Blah, blah, blah. So let's look at this. Let's look at an example really quickly, okay? A student in public administration, okay, wants to estimate the mean monthly wages, earnings of city council members in large cities in the United States. She can tolerate a margin of error in estimating the mean, $100, okay, of $100. That means what? The mean that she finds in her sample, this X bar, she's doing the same thing we've been doing. She's just giving different information, right? She has different information. She's just going about it a different way. That's all it is. Okay? So whatever estimate she comes up with right here for the average from the sample, she can go $100 each way and still consider it an accurate study. Okay? You got me? Now, she would also prefer to report the interval estimate with a 95% level of confidence. I do see a Z. Here's the formula again. I do see a Z in that formula. What's my Z going to be? 1.96. I'm not doing it on the board. I can do it on the board if I need to, but I think we're starting to get this, okay? Now, blah, blah, blah. Oh, and by the way, that $100 margin of error is that E, right? The big uppercase E. All right, so our denominator. Now, the student found a report by the DOL that reported a standard deviation of $1,000. So that might be a case where you have a standard deviation of a population without knowing the standard deviation, or that's what you would use. It's more accurate than the standard deviation of the sample, right? You want to use, because that's the actual standard deviation. But without knowing the mean. I don't know where you can find a report that did not report the mean, but did report the standard deviation. It's kind of weird, right? But whatever. This is an example of what we were talking about, and that's why we got the Z there, right? Okay. Everybody following me? So what did she do? Straight up plug the numbers in. There's nothing weird to do here. It's not a two-step problem, none of that. Plug the numbers in. And how many people did she get here? Sample size of what? 384.16. Can you survey 0.16 of a person?
No, it's very difficult.
It's really tough, isn't it? It has to be, the 0.16 of the person has to be the head because they got to be able to talk to you, right? But they can't have the rest of their body. So what do you have to do?
You just had a person.
Very good. You round up. When do you round down?
Never.
Don't round down on these, and why not? Because if you need that 0.16 of a person, that's telling you what? You need that extra whole person, don't you? Makes sense, right? Okay.
That's true.
So even if it was like 384.05, we'd still round it up?
Still round it up. Yep. Better safe than... What's the harm in counting one more? You know what I mean?
Yeah.
It's better to have it not dated than they not have it.
That's right. You know what I mean? Because you probably have to throw some of them out anyway, won't you? There's always something that happens.
That's true.
All right.
My mom always said not because I
I don't see how that's relevant.
It is relevant
whatsoever.
because you never know what you're going to get.
Oh, I see
Part
what
of
you're
these
saying.
functions.
I see what you're saying.
That's right.
I never knew that was a movie about stats.
That's right.
But now I'll see it in a whole different way.
Mm-hmm.
That was a good movie, though.
Really?
Stargate? Is that what it was?
Yeah, basically.
Okay.
It was space. So.
Yeah, that's right.
Twice.
All right, so. Blah, 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 blah. Oh, so after the means, we looked at what? Proportions, didn't we?
That's right.
So we can do the same thing with proportions, but it changes. The formula changes a little bit, doesn't it? Because what are we using instead of means? We're using the sample proportions to figure out about the population proportion, aren't we? So this pattern right here should look pretty familiar. P times 1 minus P, because where did we just see that in that formula?
Your numerator.
Yeah, it was in the numerator up under that square root, wasn't it? Remember? And that's squared, so you can see how this is the same info we had, isn't it? We're just rearranging the information. Y'all understand that, right? Okay.
You brought your N out and you put your ZE over there.
That's all we're doing. Everybody see that? Or actually, we're just bringing the N out is all we're doing, because we weren't really solving for anything last time, remember? These were P plus and minus an amount. We're just rearranging this is all we're doing, really. Okay? And again, it's just plug and play. Let's look at a quick example. So, the student in the previous example, she also wants to estimate the proportion of cities that have private garbage collectors, private refuse collectors. Okay, the student wants to estimate the population proportion with a margin of error of 10%. So she could be 10% off, right? 10% off. That's the E. With a confidence level of what? 90. So it's a little bit different now, isn't it?
Changed it up on
So that might be one you might want to memorize 90. You might see it enough to make it worth it. Okay? 99 rarely, but that'd probably be the only other one you see. Okay? 95 is 95% of the time. 90 is the other 4.9 and 4, and 99 is 1%. Okay? Now, what's the required sample size? We are literally going to plug those numbers in. But notice the Z is different, isn't it? What's that Z score this time? 1.645. Okay? Now, when you look it up, you can use 1.65 because that doesn't throw your tolerances within Connect, okay? That shouldn't, because you're usually going to 2 decimal places, right? So I don't think it should. Plus, the z-table within the, well, no, it doesn't fall right on it. Okay, so 1.645, you'll see that those 2 z-scores, it'll be right in the middle of the 2 areas, okay? But use that or 1.65, you should be fine, okay? Now, how many cities does she end up needing for this experiment to sample? 68. 67.65, let's round it on up to 68, yeah? We good?
Was point 50 in the last problem with her too? Where did that come from?
Oh, that's the, oh, you know what? That's a good question. So that's our P times our 1 minus P. So that's our proportion, 50-50, right?
Oh, okay.
The reason they use that, I wondered that too when I was looking through this. Either they do or they don't, 50-50 chance, right?
Yeah.
That's all I can figure, unless she has something else that told her that it is around 50-50. I'm guessing that's the 50-50 chance. Good catch, though.
So that
Good
would be
catch.
Every time, pretty much?
No. Well, depends on what information you have, okay?
I'm guessing the way she's doing it is just whether they do or don't have.
Where she just had no idea, where there was no kind of underlying data. But what if it said that the sample data that you pulled, no, well, you're taking a sample, so yeah, it probably would be every time. Because you're initiating this sample. Unless it says previous samples have shown that it's 75-25 or something. You see what I mean? 75% due.
So-
Unless there's some indication of some kind of previous reason that tells you should use otherwise. Yes, you should use 50-50. I saw that earlier. That's a good catch, though. Does everybody understand what he's saying? 50 times 1 minus 50. What are we saying if it's 50-50? Right? That's what we're saying, right? If there's a 50% chance that they do have private refuse collection, what is the 1 minus the do have? The don't have. What does the don't have? It's also 50, isn't it? Everybody understand that? And since we're taking a sample, we don't know what it is, do we? We have no idea. You see what I'm saying? Because we got this population over here, but the whole reason we're doing the sample thing is because we want to know about the population. We don't have any idea, so we're taking the sample from scratch. Okay? So good point. Good catch. All right. All right, this is the last idea we're going to talk about today before we get into Excel. The finite population adjustment. When do you use this? I'll have to look this up. Unfortunately, I have to admit my ignorance here. I don't know the exact line that you have to, where this is, you're going to have to use this, where this is called for, okay? So what we're talking about here is a correction factor that you apply to a z-score, one of the z formulas, confidence interval problems, yeah? Or one of the t's or any of them, okay, that we've done. Proportion, mean, whatever, okay? But you apply it when the sample size is a large portion of the underlying population, okay? And the reason for that is, if the sample, say for instance you have a population of 100 and you're pulling a sample of 50, you're using half of the whole population in the sample, it's possible for you to get a standard error, your standard deviation of your sample, outside the standard deviation of the population, okay? With one sample. You see what I'm saying? So, yeah, so, in order for that to happen, in order for your mean to be able to fall, to accurately be able to fall within your range, okay, you have to right size, in essence, right size your standard error, okay? So it's not way out here on the ends, because if you're pulling that big of a sample size, you're getting the benefits of having the large sample size without the necessity of it pulling itself back in. Do you understand what I'm saying? Let's look at an example really quickly, and I'll show you. But let's see what it says right here. Make your estimate more precise by reducing the standard error and resulting in a smaller range of values in estimating the population mean. So it squeezes in your spread of your sample is what it does, okay? So it squeezes in this, doesn't it? And it's going to ensure that you have something more accurate for where the population falls, okay? Let's do an example really quickly. So there are 250 families living in Scandia, Pennsylvania. Okay, it is a real town. Somebody in one of my other classes looked it up. It's near Buffalo, I think he said, New York. Anyway, a random sample of 40 of these families. A random sample of 40 families out of 250. Pretty large sample size given the population. Okay. Revealed that the mean annual church contribution was $450. So what is that? That's our X bar, isn't it? The mean contribution, X bar, sample contribution, was what? $450, right? And we know we're going to give it a plus that and minus that. And we're going to be a certain amount sure that the population mean falls in here somewhere. Good? All right, so we do this problem, blah, blah, blah. What's the population mean? What's the best estimate for the population mean? We know that, don't we? It's the $450. That's all we got to go off of. Develop a 90% confidence interval for the population mean. Using that confidence interval, explain why the population mean could be $445. Could the population mean be $425 and why? Okay, so we got the point estimate of $450. The standard deviation of the sample is $75. Are we going to use the z-score or are we going to use that t-value? Huh? Z-value, t-value. Why are we using a t?
Because we don't have a population standard deviation.
Very, very good. We got our sample standard deviation, which is $75, right? Okay, now, so we're going to plug it in, do all our work, right? It's going to be 450 plus or minus whatever the t is. By the way, we're using 90 here, right? So we're going to go across the top on the t table. We're going to go to 90, not 95. We're going to stop at 90 and drop it down how far? How many was it? 75 people?
40.
40 people. So we're going to drop it down to what?
39.
39, aren't we? And whatever, wherever 90 and 39 meet, that's going to be our t value, okay? Now, surely it's given on there, right? Yeah. It's a t value of 1.68, okay, times that s, which is what? Standard deviation of the sample, given to us, $75 over the square root of the n, which is 40, right? Yeah. Well, but first though, oh no, it doesn't give us that s. That s, where's the s at, or the t at? The t. It doesn't give it to us. Anyway, I don't know what that t value is. I didn't think that sounded right. But when we do all the math out, it's $450 right here, plus and minus what?
It's 1.68 times 75 over square root of 40.
Uh-huh. No, it's right here, isn't it?
Yeah, that's your t.
Oh, yeah, they already plugged it in. Sorry, guys, my numbers are dancing around on me. Okay, so,
There you
blah, blah, what's my, oh, well here, blah, blah, it should be given for the first time, though. What I'm saying, before we apply the correction factor, what was the answer there? What's the answer to this right here? 1.685 times 75 over the square root of 40, which I don't see. You see what I'm saying?
Yeah. I can try to figure that real quick. Hang on.
So right now we're looking at plus a certain value minus a certain value, which is what he's looking up right now. But what I'm going to tell you is, when we plug that correction factor in, which is this, right, what we just looked at, all it is population size minus the sample size over the population size minus 1, square root of all that, right? When we plug that in, it sucks in our standard error, doesn't it? It right sizes, it corrects for that large population, or that large sample size. Okay? So it ends up being plus and minus $18.35. Doesn't it?
Yeah, before you do the correction, it's 19.715.
Okay, so before it was 19.17.175?
715.
715, so 72 cents.
Yep.
Not as drastic of a difference as I was hoping for, but,
I may have did that wrong. Let me check.
well, that's probably right.
I entered in, I said 74 instead of 75. It's 19.98, but
Still not as big as I would have thought.
yeah.
So it's 19.98,
Yep.
okay? All right, so what's the question it's actually asking us? Could the population mean be $445? Where's $445? Where is it? About right here, isn't it?
Yeah, about right yonder.
Could it, does that fall in our range?
Oh, absolutely.
Yes, right in there. What about $425? It's outside, isn't it? So we're 95% sure it ain't there, huh?
90% sure we.
Oh, 90%, yeah? Yep. Does everybody understand what I'm saying here? Same idea, isn't it? It's just we apply, same thing we were doing. It's just when you got a big sample size from in comparison to the population, we want to squeeze in that standard error, okay? We want to tighten it up a little bit. How do we do that? Boom, apply that. I will have to look at, and I'll tell you next week, how big the sample size needs to be in relation to the population before you utilize this. Okay? Because again, that's what I'm saying, I can't remember. And don't worry, I'll edit that out of the video. I'll have the answer, trust me. Alright. Are we good? Where are you going? I said 3 minutes early. Oh shit, this is 3 minutes
It's 3
early.
minutes early.
Sorry guys, we didn't get out as early as I thought we would today. But, I hope you learned something.
Oh, yeah.
Nah.
As always.
As always. We good?